Well, thank you very much for that introduction. I hope I can live up to it. First of all, in fact, the main thing I want to talk about is something which is not quite finished. Namely, well, what you see in front of you up here is actually a drawing, or whatever they do these days, with computers, I suppose, of the new mathematics building. That's the only thing which is in color, which is not quite finished. It's finished enough that I have an office there somewhere. I can't really get into it. There's only one chair and 2 desks and a whole lot of crates. So it's not very hospitable yet, but that's partly my fault because I collected too many things in my other office. But right here will be an area tiled with a particular arrangement which is based on things that I've been doing. So I want to explain that. That's really the purpose of this talk. I'll come to the detailed explanation of what's going on there towards the end of the talk. I shall say lots of things about other architectural use of these tilings in other parts of the world. But before doing that, I want to explain the tilings themselves. So I need to go to the next picture, I think, where you can see it. The front entrance is right here. And you have to walk over my tiles in order to get in the building. And it's not quite finished. You might see some goings-on back there where it's not finished. There's some other goings-on back in front, which aren't in the picture very conveniently, where it's not finished either. That's not finished, clearly. And that one in the middle isn't finished. I think that's going to be the last tile which is placed. And in a certain sense, it's central in the whole design. But you may see some kind of irregularities as you look at it, but not altogether obvious what these regularities are. So I shall be explaining what that's all about. But before doing that, let me explain the general idea of what crystal symmetries are allowed and what aren't. And so can I move to the visualizer, please? Thank you. I'm using this kind of old-fashioned technology because that's the only one I understand. These are the crystallographic symmetries. So we have, I can point this way, I suppose, or the other way. We have twofold symmetries. A regular pattern of parallelograms will have a twofold symmetry about the center of each parallelogram. Threefold, if you have equilateral triangles, then about the center of any triangle, you'll have the whole pattern has a threefold symmetry. You rotate through 120 degrees, the whole pattern goes back into itself. Fourfold, of course, squares, that's the most familiar. And sixfold, we have the familiar pattern of hexagons. And it's a theorem, a mathematical theorem, that these symmetries are the only ones that you can have. When I say that, I mean in addition to translational symmetry. So you have to have a translational symmetry. That means you slide the whole picture parallel to itself in some directions, and the pattern goes into itself. So you want to have a rotational symmetry and, together with that, a translational symmetry. And I want to give you a quick argument to show that that is the case. These are really the only symmetries you can have. This is a sort of standard theorem. Suppose you have a pattern of points or something which isn't like a fractal, so they're discrete and have sort of finite minimum distances between points and things that you can imagine some pattern. And that pattern has a translational symmetry, so you can slide it along and it goes into itself, but also a rotational symmetry, so you rotate through 360 degrees over n, where n is your degree of symmetry, and the pattern goes into itself. So what I'm going to propose then, that you have such points of symmetry. So here's a point of n-fold symmetry, and there's another point of n-fold symmetry. You see, if there's one, there must be another, because if the whole pattern slides along, then this will go into another, will have to be another n-fold symmetry point. So it's got to have more than one. And if it's got to have more than one, there will be somewhere in the pattern two of them which are as close as possible. So I'm going to choose those, as long as it's not a fractal or something silly like that. Choose a pair of points which are as close as they can be, and that's those ones up there. Now, you see, I'm going to rotate this one by 360 degrees over n into that point, and this one in the other direction through 360 degrees over n into that point, and these two will then be closer, which contradicts this being the closest. So that's a contradiction unless n equals 2 when they're not closer, they're a lot further off. When n equals 3, they're not closer, they're further off. When n equals 6, that's at the bottom, when they coincide, so you get away with it there. In the case of n equals 4, of course, they're the same distance as before, so that's okay. But n equals 5, for example, they're closer, and anything larger than 6, they'll cross over like here, and they'll certainly be closer. So that tells you that the only symmetries crystal symmetries you can have are those ones given. 2, 3, 4, and 6. Okay. Straightforward. Okay, well, what about this pattern? Well, it has a lot of regularity to it, and it has a sort of fivefoldness to it also. In fact, you can see various regions which have fivefold symmetry up to a point, and which have translational symmetry up to a point. In fact, let me tell you that if you give me any percentage less than 100%, say 99.9%, then I could slide this picture over itself so that the pattern agrees with what you had before to that percentage, 99.9% or whatever it was, and also has the rotational symmetry, fivefold symmetry, to 99 point whatever it is. And you might say, well, why doesn't the theorem work? And the argument is, well, you go back to the proof here, and you see if this point up here wasn't a perfect one, you see, suppose it was only a 99.9% point, and that's a 99.9% point, then that's likely to lose just a little bit of accuracy. It'll be 99.8, likely. And that one's probably 99.8. So that although they're closer, they're not quite so good. So you lose a bit of the symmetry, but each time you perform this argument here, but the points may be closer. So there's a trade-off between those two things. And that's exactly what happens with this pattern. So anyway, I'll just show you that. I think it's worth pointing out a number of features of this pattern. For example, well, actually, see these rings here. I'll talk about those later. That's a 10-folded regular decagon. And every time you find one of those regular decagons, there's always 10 pentagons surrounding it. That's always the case wherever you find one there. There's another one here. Sometimes you find them overlapping, like this one and this one, and you still get rings of 10 pentagons. They just happen to go through each other, that's all. So that's a general feature. Another feature, for example, which is perhaps a little more obvious from well, it depends where you're sitting. If you're sitting up the edge, it's probably fairly obvious that you see these lines line up. Here I have, wherever you find a line in the picture, and you put your ruler along that, you just find other lines lying in that, and the density of them doesn't fall off. It doesn't matter where you do it. So the pattern has a lot of regularity about it. And this regularity, well, it's not completely obvious from the way... I'm going to tell you how it was constructed, first of all. It's constructed from something very simple. Here we have a regular pentagon subdivided into 6 smaller ones. I think it's easier if I just do it down here. Regular pentagon, 6 smaller ones with a few little gaps here. Now, what I'm going to do is blow this up so that the smaller pentagons are the same size as the original one, and then subdivide each of those. Blow it up, subdivide, blow it up, subdivide. Now, if I do that, it doesn't quite work. Let me just imagine I now have blown it up. So this was a bigger pentagon sort of out here, and this was subdivided, and then I've subdivided again. And you notice there was a little gap here, and that little gap joins up with another little gap. So we have a little rhombus-shaped hole in the pattern. Okay, now I'm going to do it again. And when I do it again, if I subdivide this, there's going to be a little gap there, so this rhombus will grow spikes. And it will look like that. Now, when it does that, I find there's just room to put another pentagon inside there. Okay? And then the next step, this will grow spikes, and you get something which looks like, well, you see. I should point out that the shapes I have, the original pentagon, this star now, which I'm calling a pentacle, that's a pentacle, and this thing I'm calling a jester's cap. Well, it's more like a jester's cap this way up. So there are jester's caps, pentacles, and rhombuses. We had the little rhombuses before. Now, when you grow spikes for each of these shapes, which you go at the next stage of hierarchy, you can always find that you can fill up the gaps with shapes that you had before. So you can blow up, fill it up with these shapes, blow it up, fill it up, and that will end up with something like this. Well, it will if you've been just slightly careful about this little subtlety which I have to mention. It's interesting because I discovered after having done this that a Japanese man had done exactly the same thing, except that he made the wrong choice here. And that doesn't lead to what you get with other things that I want to say. Now, I put a tick on this and a cross on this. See, here is the rhombus with its spikes. And I put a pentagon there. That's, remember, you see, this thing. That's the rhombus with its spikes. And I can put a pentagon either up here or down there. There's a choice. Now, what I want to do is to force one of those two choices. And if you look at this spiky rhombus here, does that go down or the top? Well, what you do is you look one side or the other, and I'm just telling you this, but it does happen, that you'll always find a pattern of pentagons like this. Except this one may be at the bottom or at the top. You then reflect in the middle rhombus, so that one goes to there. If that's on the bottom, this one, if this is on the bottom, that has to be on the bottom. If this one were on the top, that would be on the top. If you make the choice the Japanese man took, this one, then you find that the next stage, it goes wrong, whereas this one keeps going forever. And so the pattern with the subdividing, blowing up will just get bigger and bigger and bigger and cover as much of the plane as you choose. In fact, we'll cover the entire plane. Okay, now I want to show that sort of backwards now. Suppose we have a big pentagon here. I hope that most of that pentagon is on the screen. There's another one sitting up here, and another one sitting up here, and one sitting there, and sitting here, and so on. But there's a big pentagon. And what I want to do to that big pentagon is subdivide in the way I've been describing. Here we go. And then I subdivide that again. There we are. And then I subdivide that again. And you get the pattern I've just showed you. Okay. Now, where was that big pentagon? Now, you see, there's something interesting about this, that the pattern has a greater uniformity than you might have thought from the hierarchical construction. In fact, you know, I have to find it. I can probably find it, but I won't even try. It has greater uniformity than the hierarchical organization seems to suggest, but yet the hierarchy is hidden in that all the time. Now, sometimes people point out that this kind of thing was in ancient Islamic art. And there's an article here I'll show you. And there's a lot of very interesting ancient Islamic art where you see regions of five-fold and tenfold symmetry. Fascinating stuff. But I haven't seen any indication of the kind of very kind of strict structure that's gone, the hierarchical arrangement in that strict sense, or anything like that. Nevertheless, they're fascinating, but it's not so clear what the deep connection is with the things I've just been showing you. However, if you go a little bit more recently than these ancient Islamic things, namely to 1619, then we find in the works of Johannes Kepler, the famous astronomer, in a book he wrote called Harmonica Mundi, and in that book, you will find these fascinating pictures. Now, I should say that my father owned a copy of this book, and I had seen this picture. I'd seen it, although it wasn't in my mind when I started doing this, except somehow I was no doubt somehow influenced to think that pentagons are not a dead loss. You see what he's done, fascinating things with pentagons, and other things with pentagons. But this design in particular I want to point out. And as I later discovered, to my surprise, here we have that picture drawn bigger. That's the very same picture as in Kepler, including a little line there, which I don't quite know why he put it there, but he did. And now, here is my Pentagon pattern. Now, I've put some marks here, if I can find exactly where. You will see that the Kepler pattern exactly fits this, including this little line there. So what was he doing? I don't know. I suspect he was probably thinking, I mean, they didn't even know about atoms and so on, and crystals and goodness knows. I suspect that he was interested in maybe some kind of atomic arrangement, and perhaps he knew about crystals and things, and he perhaps wondered whether biological things, because you often see five-fold symmetry and so on in biology, that perhaps that was something underlying that. I have no idea. And I have no idea how he intended to continue this pattern. Various people have tried other continuations which I don't believe. I think his continuation was probably much more like what I was doing here. I wouldn't be at all surprised. But it is fascinating that he did indeed had this great interest in these things. He was interested in, there's the thing called the Kepler problem, which is packing spheres as closely as you can in three-dimensional space. And this problem was unsolved for a long time, and only fairly recently was it solved, with the aid of a computer, I may say. And it turned out Kepler was right in what he suggested. You also see there are other symmetries displayed, like these. And in fact, you find these things in quasicrystals also. I wasn't going to show you too many of these other ones. It would just take too long. I've just showing you here a 12-fold one. This is by some people, Galen and Nissen. And it's a design. Nissen is an experimental person, and he'd actually spotted 12-fold symmetries in certain apparently crystalline materials. And he showed me the diffraction pattern. It's a curious story. He showed me the diffraction pattern, and I saw this pattern of little spots where you get diffraction electrons, where they bounce off in certain directions. So where have I seen that pattern before? I couldn't think. I've seen it before somewhere. I've seen it before. And then I realized it's right here. It was this little spikes are on the corners of this little pattern in Kepler. What was he doing? I haven't the foggiest. But it's fascinating to see how much there was in that little picture, set of pictures of Kepler. Here's another one with the 12-fold symmetry. The 12-fold ones are rather nice. There are also 8-fold ones, which Robert Ammann and someone else produced. I never found them quite so attractive. I think that the 5-fold ones are nice, and the 12-fold ones are also particularly nice. So, but I'm not showing any more of those, I'm afraid. So I don't think they've been used in architecture, as far as I know. Okay, so that's the basic idea. Now there's another bit to the story, which is somewhat different, which has to do with, well, that doesn't do much, does it? Sometimes in some of these machines, you put that up and you see only what I've covered up and not this. Depends on the way the lighting works. This was a set of tile shapes. I won't go into the whole story. It was quite a long, interesting story to do with mathematical logic. And in the course of this story, an American mathematician called Robert Berger discovered a set of 20,426 shapes, which would only tile the plane. It would tile the entire plane, but only in a way which never repeated itself. And he needed to do that to show that a certain thing that actually to show that the tiling problem is not computable. That was actually what he's trying to do, but that's not part of my talk here. But Raphael Robinson, who's another American mathematician, managed to reduce this number from 20,426 to 6, you see. And so this was pretty impressive. It had gone down in steps from some other people, but this was his achievement to do it with 6. And I was talking to another American mathematician, Simon Cochin, and he told me that Raphael Robinson was somebody who liked to get the numbers down as small as possible. And I thought, well, 6, I see. I know I can do it with 5. Well, you see, These are the shapes that you get in the tiling pattern I've been showing you here. You see, you get the pentagons, the rhombuses, the jester's caps, and the pentacles. But if you want to make a tiling problem which forces this arrangement, you can do it by putting little knobs and notches on the pieces, and that forces them to fit into that arrangement. I won't try to prove that, but that's true. But you need three different versions of the pentagons, depending upon whether there's 5 other pentagons next to it, only 3, or only 2. And that's the difference between the 3 kinds of pentagons. But the thing is, you'll notice that this pentagon here has that funny little thing there on the bottom, and this thing has that funny little thing, and this has 2 of them. So all you need to do is to take that one, glue it on there, and glue it twice on there, and you've only got 5 pieces. So I knew I could do it with 5. Then I started fiddling around for a bit, and I realized you could do it with 2. And so that's the 2. And the way it works, well, I had another version first, which I'll give it to you. You have to match the colors. You can do it with little knobs and notches like this as well. But if you just match the colors, and here we have a version which is boringly uncolored, but you can see underneath is that tiling pattern. Well, I'm going to show how these others are related to the pentagon pattern here. They're all part of the same story. I have to make sure and keep these things in sight. And let's say something about the story. Well, first of all, let me mention the other one which came first, which is kites and darts. These are the kites and the darts down here. And at the top, I hope you can see, you put the kites, you mark the kites and the darts. Each dart is marked the same way, and each kite is marked the same way. And they fit together to form the tiling which I just showed you. I think it'll be better if I show you their kites and darts assembled. And here we have the rhombus, the original, not the rhombus one, the pentagons. So there we are. I think that's it. And if you look carefully, you'll see that every kite is marked the same way, and every dart is marked the same way. So this pattern of kites and darts is equivalent to this pattern. It produces this, but only with only 2 shapes. So that's how you can do it with 2. Of course, I haven't put the notches and the knobs on it. Let me do that by putting, well, there were actually, I put knobs on here with black and white corners colors, so I can do that here. I just noticed that they're opposite way from in that other picture, but that doesn't matter. So here we have the kites and darts, and I'm now going to mark the corners. And if you match those corners, the only way of putting them together is one of these non-periodic arrangements. I should perhaps make a point about this. Does that mean that the only way of covering the entire plane, that there's only one way of doing it? Yes and no is the answer to that. Strictly speaking, mathematically, the answer is no. That is to say, there are many ways of continuing to infinity. However, in a certain finite sense, they're all the same. That is to say, if you find any 2 of these complete tilings of the plane, with the same shapes, that is, and I take one of them, and I take a region, no matter how big, that's finite, I can find that in the other one. So you can't tell, ever, which one you're in. It doesn't matter how big the region is, you can always find it in the other one, infinitely many times. Okay, that's not so hard to prove, actually, but curious. Okay, you can also do it by making a jigsaw puzzle instead of the notches and knobs. Jigsaw puzzle, okay, here's one. That's a sort of Escherization, I would say. I'm not sure this will match on that. I didn't try to get them to match. Oh, that's not too bad. They might do, but I haven't actually tried that. They are about the same. You see that if I concentrate on that bird there, it's a, there you are. That one, and they won't go all the way around, but yes, there we are. These ones fit, but I'd have to find a better place to match them. But as I said, any finite region, this will be in, et cetera, et cetera. But if you want to know how to do it, you do it this way. They're really kites and darts disguised, and then there's a hierarchy which you can apply. I won't go into that here, but just to show you the sort of things you can do. Now here is the rhombus pattern. When people use it, they tend to do it without any adornments. I prefer it when you see where you are. The trouble with this, if you just take, it's not as a jigsaw puzzle, there's zillions of ways of doing it, of course, because you can tile with either one without using the other one, and there are many ways of doing that. So you have to have some rule about how you fit them together, and the rule could just be, well, it's that pattern. But that's not very economical. You could say the rule is that they have to match the stripes, which I showed you before, and so on. There's also a close relationship between the kites and darts and the rhombus one. You see that many of the lines are in common between the two. Okay, let's go back to the rhombus pattern again. And memorize that pattern. And here is a rather finer one. I hope you can see the rhombuses all right. I'm afraid there's some places where it's got a little worn, but that is indeed what it is. Of course, you see, I did these things all by hand, but of course now the computer people take over and they can make much more impressive pictures than I ever could. So that's a computer picture. I'm going to show you another computer picture. You can go even finer than that. Now that is rhombus pattern. I don't think you can quite see the rhombuses. But what you probably can see is Mauri patterns. Now it's quite interesting because you can get one of them in the middle, say. It takes a little skill to do this, and I may have lost it because you have to move the thing at right angles to where you want to move it, so it's tricky. I'm trying to get that spot in the middle. Now you see various lines going across. Those lines are the places where the patterns differ. Where they agree are the spaces in between. Now, there's another spot. Let's try that one. I'm not sure I'm getting any better at it, but I'll try. I think that the lines are further apart. Well, look, I'm going to cheat now. I'm going to use some little guide marks at the edge. Now, I'm not sure that I can get it accurately enough. It's quite hard to do. Ah, yes. You may see there, yeah. It agrees everywhere except along those lines there. And if I move it far enough away, I can make the patch where it agrees as big as you like. I think I might just try one more here. Whether I can actually find the right marks, I'm not sure. I marked the edge here to try and find it. I hope that's perhaps it. Yeah. It agrees everywhere except that one line across the middle. Except I've not found it. You can do it this way, I think, but then that's... I don't know. Let me just match the things at the edge. I think that should... Can you see it? That's it. There we are. That's it. Okay. That's the demonstration. Okay, now, let me make a point. I used to give lectures on these things a long time ago, and in the 70s. And people would say, well, doesn't that mean there's a sort of area of crystallography opening up? And I used to say, well, yes, in principle, that means you could imagine such things, but I couldn't imagine how nature would do it. Now, there's a reason for saying that, and that is that the assembly can't be in the way you would imagine a crystal to be made. Because the sort of classic crystal assembly is you have the atoms come along and sort of sit in a little ridge one by one, and then they come on another layer and another layer like that. That's a local assembly. Now, you see, the assembly is never local. And I knew this because suppose we have that pattern. These are kites and darks, and that is correctly assembled. You could continue that to infinity. If you put a kite there, you can still continue it to infinity. If I take that kite off, I'm sorry, that's a dart. If I take that dart off and put a kite here, you can still continue that to infinity. But if I put a dart there and a kite there, it goes wrong just about there. So it's a non-local feature. And it seems puzzling how you could get crystalline-type substances to grow if it is this kind of tiling. So I was sort of a bit skeptical that maybe you could have such a thing. Well, I think I want to move now over to some more of the PowerPoint images. If we could do that, please. Thank you. This is a design for a poster which was in the Mathematical Institute, where we're moving to this other building. And I don't think it's been put up in the new building yet, but the idea was to have some assembly of these tilings. These are all tilings that were given to me by people who manufactured individual tiles. The ones in the middle were given by a mathematician called Ron Graham, who I think he just wanted to play with these ideas, and he put little knobs on them so that you could fit them together only the right way. You're not supposed to turn them over, otherwise you can do it the wrong way too. He was a bit worried about these are some of his too, so you can see the kites and the darts. This kite and dart pattern is also, I have 5 different colors, and the coloring of the pattern is uniquely determined by the tiling. I won't go into what it is, but it makes the pattern is absolutely, the pattern of colors is absolutely fixed by the tiling pattern, with certain rules about it. You may be able to see things sort of jumping out at you when you look at the pattern. Here we have a rhombus version, and here we have the rules about the hierarchy, how they work. I won't bother to go into that in detail. Here we have some amusement with, I showed the birds to you. Those are the birds. These are really the birds, kites, and darts, like that. Now here you can see them as individual birds. The other side, well, not the other side, but an alternative way of coloring, it brings back the original Pentagon tiling. You notice there's a little foreign creature in the middle. There's a dog there. If you put one dog in this pattern, the entire pattern right out to infinity is completely unique. There's exactly one way of doing it. So that's quite curious. It's a little bit hard to see what's going on with that pattern. Down in the corner here, we have some actual materials. This is an actual quasi-crystal. I think they now call these things crystals instead of quasi-crystals. I'm not quite sure. The notion of crystal has extended to include these things. But you see this beautiful regular dodecahedron, which is certainly not allowed in ordinary crystallography. And here we have the diffraction pattern. These things were originally discovered by Schechmann by looking at the diffraction patterns, and if you look carefully, you see that there are pentagons and things in the diffraction pattern itself. Can we? Oh, I can move it ahead myself, can't I? There is a bigger picture of that very beautiful rhombic, a very beautiful dodecahedron, a regular dodecahedron, and with very nice edges and corners and things like that. And it is believed that the atomic arrangements are of the kind that you've seen here. There are lots of versions of these atomic arrangements that you can have, but that's just okay. I don't know in this particular case what arrangement. There's incidentally a 3-dimensional version, of course. There were 3-dimensional. I think Robert Ammann was the first person to produce a 3-dimensional version of the pentagonal tilings, but then various mathematicians discovered very sophisticated ways of generating these things by taking lattices in higher dimension and slicing them and projecting them. I don't want to go into all that here. Let me see what the next is. Okay, now let's see some architecture. This was the first use I know of any of these tilings. This was done quite soon after I produced them by a Japanese architect. I was really quite impressed with him because this thing was, there are all sorts of things in it. It's kites and darts. It's a little hard to see at first because they're decorated by certain arcs, which were suggested by John Conway, mathematician, to produce nice patterns. But here you have 2 darts, two kites and 1 dart, and there's a kite. There's a dart, sorry. There are 2 kites, 5 kites, and so on. But the architect noticed when they put this thing up that there was a mistake in it. And he insisted that they took it down and corrected the mistake. So I was impressed with that he cared about that carefully enough. But it is it's a very intriguing and interesting pattern. I was quite flattered to see this thing produced. And there's a younger version of me standing there. Now this, Storyhole in Melbourne, in Australia, they wanted me to be there at the opening. I wasn't able to go. I visited later on. It's a most extraordinary place. I'm not sure what I think of it. You can go inside and you find more of these things all over the place. So it is based on this rhombus tiling, and quite correctly done, I think, on the whole. But it's elaborated in all sorts of curious ways. So it's quite an interesting building. But let's move on. Now here we have, this must be in the Australian, I have a crib here which tells me. No, it's the one in the Science Centre, I think. There are two of these tilings in Perth. The Science Centre, I think this one's the Science Centre, that's right. And it's straightforward rhombus tilings, and you see them edge on, and they're two different, the fat and thin rhombuses are there. It's a bit hard to see them in this picture, but you get some feeling for the extent of them. And that's a shot taken from above. Yes, this is the Science Centre in a place near Perth in Western Australia. Very impressive. I think they're very nicely done. Now this is the kites and darts. This is in my old college, St John's College in Cambridge. And I think Peter Goddard, who was the master at the time, sort of liked the pun of the idea, because this is the entrance to the Penrose building. It's nothing to do with any member of my family, as far as I know, but it happens to be somebody called Penrose who designed it. And the piece of wood in the middle of the picture here is a door. It's the entrance to the library, and this is a sort of circular pattern on the floor, and the door here swings round. There's a pillar up the middle there, and it swings round. So you can't really see the whole pattern all at once, but you can swing the door around and see different parts of it. Here we have just seeing the pattern, what it looks like. So it's straightforward kites and darts. It looks very nice. Now, this is Helsinki. And I was shown this, and I was a little puzzled by it, because it just took me a little while to realize what it was. At first sight, it looks like something else. But when you look carefully, you see these triangles and that shape. They make a dart. So the darts are broken down. Let's see if I can find one here. Yes, here's a dart. That's the nearest one. There's a dart. But it's cut in two places to make smaller tiles. I suppose they didn't like they like their tile shapes to be convex. I don't know if that's what it was, but the kites are complete kites. It's a really quite big area, tiled in this way. I don't think I've ever actually seen it, but that's in Helsinki, in Finland. Okay, let's move on. This is in Stoneybrook. The Simon Centre, I think it's called. It's an institute. And on the ground, you'll see here, I'm going to go here first. Here we have the straightforward rhombuses. No adornments, just rhombuses. And here we have a view. Looks quite nice. Nicely done again. But the two kinds are both look the same. So you have to know what you're doing to see what the pattern is all about. But you see regions of five-fold symmetry, such as up here, and so on. And that region of five-fold symmetry extends to somewhere beyond it, too. So it'll do that for a while, and then something else comes along. Yes, this now is the chemistry department floor in the University of Western Australia. And this is a really big area. I went up high to look down and see if I could see any mistakes. I didn't spot any, which was fortunate. I think it's probably correct, yes. I had quite a good look at it, and I think it's correctly tiled. But you do find sometimes mistakes in these things. And there is you get some feeling for the size of it because somebody's standing there on top of it. Now the two tiles are not distinguished in their nature, but only in their shape and size. Now that's a different one. These are kites and darts. That's Carleton University. And this is kites and darts, nicely coloured, quite nicely arranged. All right, there we have a good shot of them. I'm not quite sure what the colour coding is doing, but it's interesting, looks nice. Now this is a place in India, Allahabad, where they have a big complex of buildings. And it's supposed to be, the arrangements of the buildings and the designs of the building is all supposed to be based on a big version of one of these tilings. And I wanted to get an aerial view of this complex of buildings. And I went Google Map, I had a look. And I could just about see why some of the buildings had some vague relation to the pattern. I suspect they didn't finish, or they tried to do it one way and then did it a different way. I have no idea. But it was hard to see the patterns in the large being constructed according to one of these tilings, but maybe they are. On the other hand, you see in the building, here is a kite and dart pattern, which seems to be pretty accurately done. The building itself is a 10-sided building, and that sort of reflects the 10-sidedness that you see in this pattern in the middle. So that looks quite nicely done as far as I can see. I couldn't get terribly good pictures of these things to see what was going on there. Now, here's something else. Everything I've shown you up to this point is real. I want to show you a project. This is a project for a thing called the Transbay Transit Area, which is a railway center in San Francisco. Now, I don't associate railways with the United States, but I think that's the idea, is that railways should become more important. And this big center, it was a big project, and it was advertised, and this particular company seemed to have won it with this particular design. Now, I want to show you some pictures of it, just to give you some feeling of the scale. This is the inside. The trains will be underneath, and this is just to give you some picture. All these things I say are not real, they're simulations. But the intention is that this will become reality in some time. I forget, they gave me some kind of a date. Whether I'm supposed to believe it, I'm not quite sure. But I think it was 2017, which doesn't sound all that distant in the future. I'm not sure that the tilings on the ground are anything to do with these tilings, but that's giving you a picture of the scale. This also, even more, on the top of this transit center will be a park. So this is in the day, this is the same park at night. Of course, as I say, none of this is real. Or real in the future, I suppose. That's the idea. But it's a simulation. But it looks wonderful. You have this wonderful park in the middle of San Francisco, set up above the ground level, which is down here and down there, and huge buildings which extend up. And here it is at night. So that you see. And now, this is what the sort of sides. On top of this is that park. Then you see that area that we just looked at before with the people walking around. And then there's this skin thing here which wobbles around. And underneath that would be the railway station. That would be the last thing to get built, I suppose. The railways are considered, well, I suppose that's a big project to get the railways. You've got to put them right across the states. But you will see, if you look carefully, at the cover that they've used. Now, it's not flat, which presents curious problems. But here you see more clearly. They have these panels, and they have the rhombus tiling on the panels. Now, the reason they did this, apparently, is that if they chose a regular tiling, then when they joined the panels together, you saw that they didn't match, and it looked dreadful. So they thought it would be a good idea to use these tilings where you wouldn't know what was happening anyway. And so you wouldn't spot how they didn't match along the edges. Of course, and then they said, well, this is a nice seamless construction. And the architects came across and visited me in Oxford and all this. They're very delightful people. And I said, well, it doesn't quite match, does it? They said, well, yes, we know that, but thought it didn't matter too much. So I said, well, there are two things you can do here. Now, you see, it's not flat. That was their problem. And so you have to have a curved surface, intrinsically curved surface, and you want to have a tiling which actually works on a curved surface. And so they thought they'd fiddle it in this way. So I said, well, actually, you could make it so that it matches. Well, you see, they have these seams here between the... OK, those aren't supposed to match, because the things might expand and contract, and then you want to have a gap here. However, all these other ones are supposed to match. So I said, well, you can do it if you don't mind slight changes in the size. So you can have a conformal map, which means you locally they are the right shape, but the sizes can vary just slightly. And they said, we'll do it. So that's what they're going to do, I think. OK, now the last thing here I want to show you, coming back to Earth, this is real now. This is real. This is the tilings that we have at Wadham College, my college, and these are straightforward rhombuses, but you see I insisted on having something which tells you that whether you match them correctly. So you have these little, they're two tile shapes, the big one, the fat one and the thin one, and every fat one is marked the same way, and every thin one is marked the same way, and you've got to match them. And then you get these non-periodic patterns. Well, I'd been to they were laying these things, and I'd been to a play with my wife, and we came home one day and said, oh, they're laying these tiles. It would be nice to see how they're getting on. They've pretty well done it. So I went and had a look, and it looked very nice. I had a somewhat uneasy feeling. So I went up higher on a little higher level. I looked down on it, and I had even more of an uneasy feeling. I couldn't quite place what it was. And then I looked right over at the edge. The builders had put an extra tile in. They could see it would fit. Another one would fit just at the edge. It would match perfectly, and it would fit. But if you put that tile in, somewhere in the middle of the lawn, the thing would go wrong. It wouldn't go wrong. And we weren't having that. So they had to pull it out, even though the lawn, of course, is a lawn and you don't see this pattern. Anyway, this gives you one version of how to mark tiles. But I thought, since we're having this new building, this wonderful new, it really is an impressive new building, I must say. And they were going to have one of these tilings up there. And I thought, well, let's have something different. So I'm going to show you something different. Let's go back to this original tiling. Go back to this. I pointed out that we did have, in this pattern, lots of these nice little decagons and then rings of pentagons around it. Now, suppose you take those decagons. Well, let's do it a little bigger, I think. Oh, dear. Yeah, here we are. That's it. It's here. Yes, it's transparent, and it's just a colour. I can't see it on the table. That's it. Here we have it. That's the next version up. One version up. OK. It's the same thing. You've got these little... Here we have the little decagons, and there's a big decagon, you see. And where we have the little decagons, remember we had this ring of pentagons. You also sometimes get a bigger ring of pentagons. Here we have pentagon, rhombus, pentagon, rhombus, pentagon, rhombus, all the way around, and that's the sort of feature you get. Now, when you go to the bigger version of pentagons in the hierarchy, you see a bigger decagon here, and then you have my ring of pentagons around it. Okay, so we get these rings. And I thought it would be nice to have those rings featuring. I'm going to take this one out, I think. Make it clearer. So I'm going to mark all those rings. And I'm going to I have to do it the right way up, this way up, that's it. Those rings just slightly further out for a reason which, well, let's say it makes it look a little nicer, what I want to do. But there's a mathematical reason too. Okay, those are the rings. All I'm done, I've just drawn these rings in where you have them. Just outside the decagon and going around the pentagons, okay? Now, the trouble is that if I try to mark those on these tiles, they're not all marked the same way. So I've got to have a few more arcs to make this. Now I've got to mark this the same way around. Yes, that's it. That's it. And if I put these two together, what do we see now? Well, we see a sort of fattened out version of this pentagon tiling, etc. Remember, we've got pentagons. Well, they look funny shapes. They are pentagons. There's a pentagon. There we have a funny shaped one. There's another pentagon. And here we have a jester's cap, you see, but sort of squashed, funny way. And here we have the rhombuses. And here we have the pentacle. So it's the same pattern as before, but sort of swelled out in funny ways. Okay? Now, I need to fill that out just a bit more to make it, well, I think it's best if I put the rhombus pattern on there, which is here, that I can find. Remember, it sort of underlies this pattern. And you see that every rhombus has the same design pattern on it. So if you marked the rhombuses in that way, so that the thin ones just have two little circular arcs, and the fat ones have two circular arcs which cross each other, intersect. It's the same everywhere. You just need two kinds of tiles marked in this way, and then you will see this pattern of circular lines coming out at you. And I thought it would look rather nice. In fact, there was something a bit fortuitous about it, because either you see the pattern in such a way that the rhombuses are quite obvious. I didn't want that. I wanted it so you didn't see the rhombuses very well, and you saw that pattern, which I rather liked. And it's a bit surprising that you get that quite subtle pattern coming out from just two basic shapes. And they'd done this. What they have, these are made out of granite, I should say, the tiles, and the arcs are inlaid stainless steel. So it should look rather impressive when it's finished. Now, they had some samples of this in front of the old mathematics building, and I'd been in Edinburgh, and I came back late on the train, and I had a look at these things. It wasn't very late, it was quite light. And I looked at the tiles, and the two tiles look completely different. The fat and the thin rhombuses look quite different. I didn't want that. And the circular arcs didn't fit together. They looked horrible. Well, the reason they didn't fit together is it was a sunny day, and they'd been what are called combed. And that means that the light hits them in a certain direction, and then it shines at you. But if you're not in that particular direction, then they look dark. So that if the tiles are oriented differently, then the arcs will, a dark arc will join onto a light arc, and you lose the pattern completely. So I thought that looked dreadful. As you look at you just see the two rhombuses instead of the pattern. Well, they said the solution to the combing problem is don't comb it. So they do what's called polishing it instead. And that's not directional. So that should work, I hope. The other thing is the fact that the tiles look completely different. I came back a couple of days later and looked at them again, and then they looked exactly the same. And I thought, what on earth's going on? Are these different tiles? Have they gone back to China to get new granites from? No. It occurred to me the difference was the first day it had been wet, it had been raining, and the surface texture and the type of granite is slightly different. And when it's wet, they look quite different. When it's dry, they look the same. So this is wonderful. It gives you a new perspective. On the wet day, you look at it, you see one pattern. On a dry day, you look at it and see a different pattern. So I thought that's quite nice. Okay, let's get back to the PowerPoint, please. Well, this is actually where the architects were trying to work out the design. It's just showing the pattern. That's all this is doing here. You see, the arcs are in red. They said, don't worry, it won't be red. It'll be in stainless steel. And the tiles look quite different. Don't worry, they won't look that different. But it is quite useful to see this pattern because you can see this you can't see it so well, but there is a sort of central point here. And there we have a circle. You see, that's one of the many circles. You've got circles all over the place. And just outside that, you see this bigger floral arrangement. Now you see lots of those all over the place. There's right round the edge, you see, there's several all the way around. There's one, there's one, there's one, there's one. So we wanted to have this in the center and this, so that But the tiles are such a size that you can actually see these other ones. There are other ones right further in, too. There's another one there. So there's lots of these bigger rings. Oh, thank you very much. Yeah. I'll use the green one. It works, I think, a little clearer, especially on red here. So here we see that floral arrangement, and then we have bigger ones like that one here. I thought it might be quite nice because mathematicians' children could come and walk along the patterns and see if they get back to where they started. Some of them do, some take a mince, then they sort of go off the edge somewhere. I think there's a nice theorem waiting to tell how many different kinds of patterns there are before they close up. So it's nice to look at, and that's the idea. Okay, perhaps we could go back now. Oh, no, sorry, not go back to anything. Here we are. So this is the latest, not quite the latest, but almost the latest they've done. A little bit not quite finished in the top up there, and little things not quite finished there, and some area here which is not quite finished, which you can't see. I think it's quite, yes, now this is a wet passage. I think that's been wet, yes, because you see the difference in the tiles there. The other one, I think, was probably quite dry, yes, so there you can't very easily see the difference in the tiles. This one shows the stainless steel. It does seem to show up very nicely, I think. So this is, the white is just some cover that they put over top of the stainless steel. They don't want to take them off until, I think, till the official opening. And then you will see the actual stainless steel and how they join up. So I think it should look pretty impressive. Is that the last one? Oh no, here we have the view. That's the entrance, the main entrance to the building. It's a stunning building, I may say. And it's all partly, the design was geared so that the Radcliffe Observatory, which is a very wonderful building, which is sort of revealed now, it was all hidden by all sorts of other buildings previously. And not only can you sort of see it, when you get further back, you can see the top much more clearly. On the other side of the building, you could see it very clearly. And from the common room, you see, they designed it so that the building is in two halves here, with a connecting room, which is entirely transparent, so that you sort of can see through it. But it's really a wonderful common room in there, where you can sit down, you have a beautiful view of the Radcliffe Observatory at the back, and you can see the tiling from the other side, so that's nice too. Anyway, I think that's the end of it. Thank you very much.